today, and today we have a speaker, Georgy Ryabov, with a talk about construction of stochastic flows.
Okay, do you see my screen?
Yes, we see.
Yes, okay.
Yes, everything is okay.
Okay. In today's talk, I will speak about construction of strong stochastic flows, starting from consisting families of endpoint motions. And this work is based on our ongoing discussions with Olivier Reymond. So the object of my investigation is a stochastic flow. I will consider a locally compact separable metric space. And by a stochastic flow, I will understand a family of random mappings of space M that satisfies well, a number of properties. So it is measurable in omega and x. It satisfies the evolutionary property. It has independent and identically distributed increments. And the last two properties are continuity in time and in space variable. So here, the second property, note that it holds almost surely for fixed R, ST, and X. So exceptional set can depend on time and space variable. With every such stochastic flow, one can define finite point motions. The probability from point X will be in a set B. It is a transition probability on m to the power n. It describes the joint motion of n points in the flow. And one can verify that Pn is a Feller semigroup. It is consistent and coalescing. So consistency means that n point motions define k point motions when k is less than n. And coalescence means that if we consider trajectories that started from same point, then they cannot separate. The theorem of Lejeune and Reymond states that there is a one-to-one correspondence between sequences of transition probabilities, in the sense that we just defined, and stochastic flows of mappings on the space M. Today, we will be interested in a strong stochastic flows. And I will assume additionally one more property. So this last property, it implies continuity of trajectories in the flow. Okay, so by a strong stochastic flow, I will understand a flow such that with probability 1 for all RSTX, we have evolutionary property that holds without exceptions. I will not mention all possible results, all known results regarding existence of strong flow, because there are many such results. Just a classical one, it is a result of Kunita. And some examples that are related to our work is some Howitt-Warren flow of kernels, some singular stochastic differential equations. So these are cases when the existence of a strong flow is known. Also, in our previous talks, we discussed existence of strong flows among coalescing stochastic flows on the real line. In general, existence of a strong flow that is defined by Feller consistent semigroups, it is an open problem. So I will now describe the idea of the approach and then formulate some results. So I will work in the space of paths in the space. By X, I will denote the union of all continuous trajectories with values in M. Union is taken over all possible starting points, starting moments of time. So each element of the space X is a continuous function. Its starting time I will denote by I of F, and we can consider an extension of this function to the all real values. With respect to the metric D, the space X is a complete and separable metric space. So this metric, convergence in this metric means that starting moments converge and trajectories converge uniformly on compact intervals. Now, what I'm gonna do is I will take a countable number of paths from space X and try to extend them to a flow. So this is the first definition. Consider any sequence of continuous trajectories in X. By I of S, I will denote trajectories that started before time S. And ISK will be trajectories that started before time S, and at time S, they belong to the set K. Also, this is some notation for restrictions of functions phi n. Okay, and now the definition. I will say that phi n is a skeleton of the flow if we have following three conditions. The first condition says that these trajectories phi n, they really must come from some flow of mappings. So if phi nt and phi mt are equal, then these two trajectories must move together in the future. A second property is that at any time s, values phi and s form a dense set in the space. And another property, the third property is that trajectories that at time s belong to a compact set K form a relatively compact set in the space of trajectories. So this definition is not random. Okay. We mentioned that XD is a complete separable metric space, and hence sequences in this space, they admit a measurable selection function. On last talk, we proved lemma that there exists a measurable function from space of sequences of paths into the space of paths, such that when this function acts on a relatively compact sequence, the value is the limit point of this sequence. So in the since the space of paths is a complete separable metric space, there exists a measurable selection function, and I will fix it now and till the end of the talk. Okay, and with the help of this function, I want to extend the skeleton and get a flow. So let epsilon k be some sequence that decreases to 0. And for any point Sx, I introduce two objects. So first is a sequence of integers. So nksx, it is the number of the first trajectory that started before time s, and at time s, it was in the neighborhood of x, in the epsilon k neighborhood of x. And phi ksx will be the restriction of this trajectory from S to infinity. Okay, so it looks like this. I have some countable set of trajectories phi n. I have some point with coordinates sx. And then first I consider some bigger ball around x. For example, this one. And this will be the number of trajectory nsx1. So this is the first trajectory that arrived to the epsilon1 neighborhood of x at time s. Then this will be nsx2 and so on. After that, I apply a measurable selection function to this sequence of trajectories. I apply it to a sequence of restrictions after time s. By assumption on the skeleton, this sequence of restrictions is relatively compact. So the value that I get, it is some limit point of these approximating trajectories. In particular, it is a continuous function, and it starts from x at time s. Okay, so now I want to formulate some conditions under which the constructed object will be a flow of mappings. So first, some simple lemma. The sequence of integers that approximate a trajectory at time s starting from point x, it is a non-decreasing sequence of finite integers. If this sequence equals to some value m starting from some point, it means that the point sx actually belongs to the skeleton. And all approximating trajectories, they equal to one trajectory starting from some moment. In particular, we have that psi stx is equal to phi mt. If the sequence nk converges to infinity, then the point sx is not on the skeleton. And the last observation, it follows from previous ones. So if I consider a point on the skeleton, then approximating trajectories, they must stabilize. And as a value of psi sx, I get actually the trajectory from the skeleton that starts from this point. Still, we need some additional assumptions to prove the flow property. Okay, so by ksx epsilon, I will denote the closure of all trajectories that were in the epsilon neighborhood of x at time s. So again, by our assumptions on the skeleton, ksx epsilon is a non-empty compact subset of space of trajectories. Then the intersection of ksx epsilon, it is also an empty compact subset of trajectories. And the trajectory that is given by measurable selection mapping, it belongs to this set ksx. However, it may happen that this set KSX contains more than one point. This exceptional set will be denoted by E. And in the next result, I give some sufficient condition on this set when the flow psi is a true flow of mappings. The condition is the following. Suppose that if at time t the value of the mapping psi stx belongs to the set E, then I must have some approximating sequence from the skeleton that infinitely often hits this point psi stx. Okay, so I will draw this. So we have Sx. We constructed some path that starts from this point and assume that we have here at time t, we have a point ty from the set E. So it is like a bifurcation point. Then I assume that I can approximate the previous trajectory by trajectories that at time t, they exactly hit point y. So this is the assumption on our set E. If this holds, then the family psi st is a flow of mappings, in the sense that we have evolutionary property holds for all st and u. Okay, so
here there is no probability.
No probability, yes.
Could you please one more time repeat what does this mean?
What? I'm sorry.
Could you please explain one more time this picture?
So the picture is means the following. So we have we constructed some trajectory that started at time s from point x, and assume that some point on this trajectory is in the set E. Then I must have trajectories from the skeleton that approximate the first trajectory, and they exactly hit this point at time t. So I assume existence of a sequence phi and I that converges to psi s, and that is equal to y at time t. So this is psi st is equal to y.
But that is this a moment of the first hitting or not?
No, they can hit earlier.
Okay, okay.
So let's verify this result. Okay, so I want just to check the last equality that holds for all STU. So let's let us fix some 3 moments of time and fix some x, and by y I denote psi st of x. So the first case, assume that this point ty is not in the set E. We know that some sequence from the skeleton approaches function psi sx. The convergence is uniform on compact intervals. In particular, the value at time t converges to y. In particular, for large enough I, all these trajectories, their restrictions from t to infinity, they belong to the set kty epsilon. And now we know that the intersection of these sets K, they consist from only one trajectory. We know that the sequence phi K is relatively compact, so we necessarily have the convergence of restrictions phi Ki to psi t started from Y. And in particular, psi ty of Y, it is equal to this limit at time u, but this is the same as psi su of x. Okay, and the second case assume that this point ty belongs to the set E. By assumption, we have some approximating sequence of trajectories that hits Y at time t. Then from the simple lemma from the beginning, we necessarily have that psi tu of Y is equal to phi and I of u. And this allows us to conclude. Because since we have hitting of Y at time t, all approximating trajectories, they must coincide after time t. And these considerations, they prove this theorem. Now, let's relate this to stochastic flows. Assume that we have a compatible sequence of coalescing failure transition probabilities. By psi zero, I will denote the weak stochastic flow that was constructed by Lejeune-Raymond. Then let us fix some sequence of points in Sn, Xn. So this will be a sequence of starting points, and consider the skeleton which is constructed from trajectories psi zero, started at these points. If assumptions of theorem 1 are satisfied, and if every point ty is almost surely not in the set E, then the flow that I constructed is equivalent to flow psi zero in the sense of these flows have same finite dimensional distributions. In particular, psi will be a proper stochastic flow. The proof, it just follows from the fact that since ty is not in the set E, then with probability 1, I have the convergence of approximating trajectories without any subsequence. And then, well, here I showed how to calculate one-dimensional distributions. Okay, we just take the sum in all possible values of indices of approximating trajectories, and we make use of the fact that these approximating points, they converge to X. Okay, so now I go to the second question, is how to guarantee sufficient condition from theorem 1. It turns out that if we have an instantaneous coalescing condition, then we can apply theorem 1. By instantaneous coalescence condition, I understand the following. So for all s less than t, the set of values at time t of trajectories that started before time s is locally finite. So in an arbitrary positive amount of time, the family of trajectories coalesce into a locally finite set of points. And then we can, I will show that we can apply theorem 1. In particular, psi st will be a strong flow. So the proof is the following. I only have to check the case when a point ty belongs to the set of bifurcation points. Okay, some neighborhood of point Y is compact. Hence, this neighborhood contains only finite number of points from trajectories that started before time s. And now if we consider the approximating, the sequence of approximating trajectories from the skeleton, then for large enough indices ki, values of these trajectories, they belong to this ball by epsilon. But the intersection of by epsilon with the values of trajectories is a finite set. So we must, starting from some point, since we have convergence, we must be equal to some point yj. And this shows that exactly how sufficient condition from theorem 1 is satisfied in this case. Okay. The next question I want to discuss is, so now I will specify the space. We will consider metric graphs, and I will show that in this case, the instantaneous coalescence condition even implies even more. So consider a metric graph. It is the locally compact separable metric space such that we have some countable set of vertices, and we have a partition of the complement into some open sets, and each open set is isometric to an interval, maybe bounded, maybe unbounded. So with each vertex we denote, we associate the set of edges that are adjacent to this vertex. Okay, and we have, by d of v, I denote the number of adjacent edges. If a point is not an edge, we can assume that it is like an, if a point is not a vertex, we can assume that it is a vertex, and with d of x is equal to 2. Now consider the metric graph and the sequence of paths in this metric graph. Assume that we have first condition, it is a coalescing condition. Second is a locally finite condition. And the third is so that we have a dense set of points at every moment of time. Then phi n is a skeleton in according to our definition. So here the only thing that is missing is a relative compactness of trajectories. I will prove that having these three conditions, we also have relative compactness of trajectories that started from a compact set.
Georgi, could you please explain me, what do you mean relative compactness of trajectories?
We have, I will show in the definition of the skeleton, we have three properties. And the third one means that if I consider...
M is a compact, or not. K is a compact, I see.
K is a compact in M, and this is a sequence of trajectories that were in K at time S.
I see.
So now I assume, instead of this, I assume that I have this instantaneous coalescing condition, and I will prove relative compactness. For the proof, it is convenient to introduce the notion of simple neighborhood. Maybe it's simpler to draw a picture. By a simple neighborhood of a point V, I denote the following. So I consider all adjacent edges, and on each edge, I choose a segment. Then this set, it is a neighborhood of point V, and I will call such sets as simple neighborhoods. When a point is, when a point X is on the edge, its simple neighborhood is just the usual neighborhood as a point in the interval. Okay. Now let's do the following.
Jürgen, I forget. M is arbitrary metric space, or is it?
M is a metric graph.
Metric graph.
Mm-hmm. Okay, now one more construction that I need. Again, let us consider some point on the metric graph. Consider all adjacent edges and consider some simple neighborhood. Since we have a property that trajectories form a dense set at every moment of time, we can find trajectories that for a small amount of time, they each of them belong to a fixed edge. And as a consequence, if I consider a simple neighborhood formed by these trajectories, then for every t, it will be really a simple neighborhood of x. And now how we prove relative compactness. When we live during some small time, trajectories they do not oscillate much around x, and after a small time we'll have a finite number of trajectories. So to make this precise, consider a compact K, and for every point in this compact, we can consider a simple neighborhood of this point formed by trajectories from the skeleton. Then we can consider a finite cover of K, and it follows that we have some time, we have some moment of time such that K is covered by a finite number of simple neighborhoods, and it is true for all T from S to S plus some delta. Okay, now we have two observations. First of all, the values of trajectories at time S plus delta over 2. It is a finite set because we have a locally finite condition, and because this set is a subset of the union of simple neighborhoods. Hence, we can enumerate its elements. Now, for these elements, we have equicontinuity. Okay, and this is almost all, because now when we consider two moments of time, t and u, we consider two cases. If t is after moment s plus delta over 2, then the trajectory phi n is one of a finite number of trajectories for which we choose for which we have estimate on continuity. And if t is less than s plus delta over 2, then both points phi and t, phi and u, they belong to some simple neighborhood. And then, well, the oscillation by construction is less than 2 epsilon. So we have equicontinuity, and at time s values are in a compact set. It means that we have a relatively compact set of trajectories. Okay, so for metric graphs, we have that locally finite condition. It implies relative compactness, and it implies the strong flow property. Now I formulate a sufficient condition to have this instantaneous coalescence property. By P2, I will denote the joint distribution of a two-point motion in the flow. And sufficient condition is the following. So assume that we have some positive constant C and some positive P, such that the probability that two trajectories have met before time C times distance squared is greater or equal than P. And this estimate is uniform for all X and Y. Then with probability 1, for all S less than T, a set of values at time T is locally finite. This condition appeared in the paper by Evans, Morris, and Sen. However, they applied it in general to discontinuous processes, and for them it wasn't enough. So they have additional assumptions. It turns out that if we work with continuous processes and if we work on metric graphs, then this is enough. Also, in their approach, the space M was compact and it was essential. In our case, it is not essential. So M is not necessarily a compact space. So again, in the proof, I will use the notion of simple neighborhood. So first, assume that we don't have a locally finite condition. Then some simple neighborhood contains infinitely many points at time t that started before S. Now we do the same construction as before. So let this be our simple neighborhood. And we can find trajectories from the skeleton that bound this simple neighborhood for during some time. And also we can assume that they themselves, they are contained in some extension of initial simple neighborhood. So the observation is if we have infinitely many points at time t, then during some interval before time t, we also must have infinitely many points, and they cannot approach outside the extended simple neighborhood. Otherwise, they will coalesce with the bounding trajectories. So the observation is that I have infinitely many points that live for some time in the set K. So they start in the compact set K and they live in the compact set K during some time. Okay, and now we will estimate the probability of this event. Denote the maximal length of simple neighborhood by R, and consider any configuration of points in the compact set K. By tau n, I will denote the first meeting time between between corresponding trajectories. Each segment of the simple neighborhood I divide into n-1/m segments of equal lengths, and the length of each segment can be bounded by 2mr/n. So in general, I have more points than segments, so at least 2 points, they belong to the same segment. And this allows to make the following estimate. The probability that the first meeting time was after, so this quantity, j is some integer, c is a constant from our condition, and this is the length of the small interval squared. And if this happens, then in the initial configuration, we have two trajectories that were close of the rate 2mr/n, and they cannot meet. So this gives probability 1 minus p. But after this, we have again a configuration of points in K. So we can repeat this estimate. Okay, and once we have this inequality, we deduce the bound on the expected time of the first meet for these trajectories. So the expectation of the first meeting time under the condition that all trajectories lived in the set K, it is bounded by c/n square. If we have at least n0 points, if we have at least n capital points at time A, and if we have at least n0 points at time B, then we cannot have more than n capital minus n0 consecutive collisions. So this probability is bounded by 1/b minus a. This is like this is from Markov inequality, and then the sum of expected times of consecutive collisions. And we get a bound which is uniform in n capital, and it converges to 0 when n0 goes to infinity. So we cannot have infinitely many points at time B. Okay, now in some very simple cases, we can get proper estimates. For example, when we have independent Brownian motions, then okay, for any C, we have an estimate. Also, when we have, for example, reflected Brownian motions, we also have such estimate. So this, once again, this proves the existence of the flows. Some more interesting, so we tried to combine two cases with reflected and independent Brownian motions. It is some kind of degenerate Walsh-Brownian motion. I consider the real line as the star graph with two edges, so the positive half line and the negative half line. And at 0, I have a reflection to the positive half line. In this case, when I start from 2 points from the positive half line, then I have the usual bound on the meeting time. If 1 point is negative, 1 is positive, then I still can get some estimate which is uniform in X and Y. And again, so here is square. Yes, y minus X squared. When both are negative, we don't know if we have such an estimate. If we can bound the probability of meeting uniformly in X and Y. But probably we don't need it because from the proof of the last theorem, it is enough to consider, for example, such interval as a set K. And when we consider 2 points that start from this interval, okay, if they are of different signs, then we have an estimate. And if they are of the same sign, then there is a very small probability that they do not exit K. So I think that such considerations can give maybe not estimate of this type, but they can prove locally finite condition. Okay, so this is what I wanted to discuss about metric graphs. And in the beginning of the talk, we have a general property with the set E. And this property was designed also to deal with cases when we don't have instantaneous coalescence. In one example, there is one example when theorem 1 works and when we don't have an instant coalescence. So this is an example with the Tanaka's stochastic differential equation. And its finite point motions of the coalescing flow of solutions are have the following structure. So they move like this. They form some lenses and the only bifurcation points are at the beginning of the length of the lens. So when we have a bifurcation point, since this is a one-dimensional example and we have ordering, then we can approximate from below by trajectories from the skeleton, and they necessarily will hit this bifurcation point. So in this example, we don't have instantaneous coalescence, but the sufficient condition from theorem 1 is satisfied. And another example with the so-called interface SDE. So this is a stochastic differential equation, which is W1 and W2 are independent Brownian motions. And solutions to this equation, they have excursions of W1 when they are positive and excursions of W2 when they are negative. In this case, it is easy to check that if I start solutions from a dense set of points, I will get a skeleton. Here, maybe the relative compactness must be proved. The idea is that increments of every solution is given either by W1 or by W2. So in this case, we can prove relative compactness. And probably in this case also the sufficient condition of theorem 1 will be satisfied, because again here the only bifurcation points are when x is equal to 0.
Georgi, and I don't know, is there a strong solution to this equation?
Yes. Yes.
And who proved it?
Lejean and Raymond. This is the reference. Okay, so this is probably all that, okay, not all, what I wanted to say, that two remarks. So the first remark is that for our approach, it is important to prove a relative compactness of the family of processes that are given by coalescing failure transition probabilities that started from the compact set. Probably it is some, probably it can be proved in all cases, so we don't know. And the second is our condition on the set of bifurcation points depends on the measurable selection function. hence,
what does it mean?
It means that we started when we formulated this condition, we wrote this assumption. So S less than T and Y is equal to psi ST and Y Ty belongs to E.
Mm-hmm.
So this point Y, it is already obtained using the measurable selection,
Mm-hmm.
which was in some sense arbitrarily chosen. So maybe if we do this selection in a more proper way, maybe we can get also this condition for free.
Mm-hmm.
So this condition is true or not, depending on how we do measurable selection.
But you have examples of this measurable selection related to some epsilon net on the compacts, as I remember.
Yes. This measurable selection, it is done explicitly on the set of sequences.
Mm-hmm.
So, and then we can map every Polish space into this set of sequences and apply the existing measurable selection there.
So the condition depends on the way how we map this Polish space to this set of sequences.
Yes, or we can say it in a different way. The mapping is organized by some epsilon net, actually.
Yes. Mm-hmm.
So it depends on how we map a function into its distances to points from epsilon net.
Mm-hmm.
And then we choose some closest one and so on.
And you think that there can be a big difference between different choices?
I'm not sure, but
formally.
But it can. So now this assumption depends on how we do measurable selection.
Yes, I understand, but okay.
So maybe we can agree that if we hit some point like many times before this, yes, then we can then we have to choose this.
Mm-hmm. Let's see.
Okay, and your statement about measurable selection, is it abstract statement in just complete separable metric space or in your space of trajectories?
It is true in every complete separable metric space.
Mm-hmm. And I have also another question. Can you consider like Walsh-Arrachia flow on a graph? So before points meet,
yes,
they move independently like Walsh-Brownian motions.
This is we want to consider it.
And so what is the problem in a proof? So what have you to verify? Is this condition about probability of coalescence?
Yes.
Mm-hmm.
This probability will be enough to check this one.
Mm-hmm.
Or maybe something also one can check this condition and also that together with the condition that the trajectories didn't leave some compact set, if it helps. Also, any power of bigger than 1 will work, not 2.
And can you simplify this condition for this motion? If you take, for example, x-axis 1 or y, you see you have both 2 points, x and y, and distance inside. Maybe
Yes.
it is possible to use some. So
Scaling, you mean scaling, yes?
But yeah, some scaling, but to prove for maybe that just only one probability for fixed x is greater than something.
Maybe. This is an ongoing work now.
Georgi, also let me ask you about this again, the same slide as you showed before, with this condition of, yes, exactly. It seems from the proof that when you have this condition, you can also prove the finiteness of the total time of free motion in this system. Because you have estimation of the on the distribution of the time of the first heating in the system, and it is geometric. Something I think that maybe it can be useful just to get statement about the finiteness of the total time of free motion.
So we.
Yes.
The last estimate is it is uniform in the number of starting points.
Yes, yes.
So probably yes.
Because based on it, you can say something about the structure of the flow, saying some like absolute continuity theorem or something.
Mm-hmm.
Okay. Okay.
And
okay. So
one more question.
Yes.
You have about same condition. So is it possible to construct flows, maybe not on metric graphs, but say in R2, if you have similar estimates of time of coalescence? Because
yes.
Yes,
because if you have locally finite condition, it implies.
But you have to find such processes.
Okay.
Yeah. Okay.
And this metric graph, so does it have finite number of vertices or infinite?
At most countable.
But is it possible that all vertices are concentrated, say, around 0?
No.
Locally finite, yes? Locally finite number of vertices.
The set the set of edges, each edge is an open set in the metric graph.
The set of edges?
In some sense, when we consider distance between points on different edges, then we have to take the sum of distances.
Yes.
So they will not concentrate, I think.
Okay.
Okay. And let me. I understand the last question. So we have an assumption that that the number of adjacent edges is finite at every vertex.
Okay, if there are no other questions, then thank you for your talk. And next talk will be, next speaker will be Alexey Rudenko with the talk about the intersection of some functionals from Brownian motions and Carnot group. Okay, so today we finish our work. Bye, everybody.